Let's look at how to do a two-sample z-test of proportions, or two-prop z-test, in Minitab. Here we have a dataset on different people who started the process of getting the Gardasil vaccine, which is a vaccine that needs to be taken in a series of 3 shots, completed over a specific time frame. We know their ages, how many shots they've received, and whether they've completed the vaccine sequence, where a 1 indicates that they successfully received all 3 shots in the correct time frame, and a 0 indicates that they either didn't get the right number of shots or didn't get them in the right time frame. We might be interested in the question, is there a difference in the proportion of all 11 to 17-year-olds who complete the vaccine sequence compared to the proportion of all 19 to 26-year-olds who complete it? For example, maybe the older people who get this vaccine are more responsible, so they're more likely to complete the vaccine. Or maybe younger people are more likely to complete it because their parents are there to remind them and drive them to their medical appointments. To help us answer this question, I've created an extra column called Age Group that equals 1 for all of the people who are between 19 and 26, and equals 0 for all the people who are 11 through 17. Our hypotheses for this test will be the null hypothesis that the proportions are equal, and the alternative that they're not equal. We can start by making a table summarizing the data. We can do this by going to the Stat menu and choosing Tables, Cross-Tabulation, and Chi-Square. We have the raw data, or of categorical variables, and we can choose which variable we want to have be in the rows and which variable we want to have be in the column of our summarized table. I'll use whether or not they completed the vaccine sequence in the rows and their age group in the columns. And I'll display the raw counts of how many observations are in each category. Click OK, and our table appears in the session window. Here, you can see that the columns represent the age groups. We have 50 people in each of the 2 age categories. The rows represent whether or not they've completed the vaccine sequence. So in this data set, we had 30 people who successfully completed the vaccine. Of these, 20 were in age category 0, the younger category. So it looks like younger people might be more likely to complete the vaccine. Let's check this out by doing a hypothesis test. We can do this by going to the Stat menu, Basic Statistics, and to Proportions. In our data set, all of the data is mixed together. We don't have one column with all of the young people and a different column with all of the older people. So we'll choose both samples are in one column. Then click in the box next to Samples. This is the variable whose proportion we're interested in. That is, whether or not people completed the vaccine. In the box next to Sample IDs, we'll choose the variable that we want to use to make the groupings into 2 different samples. That's the age group column. Then click on Options. We're doing a hypothesis test, so we can leave the confidence level at 95%. Our hypothesized difference should be 0. That's because in our null hypothesis, if we subtracted the proportion of those 19 to 26 from both sides of the equation, our null hypothesis is equivalent to the idea that the difference between the proportions is equal to 0. And our alternative hypothesis is that the two differences are not equal to each other. And finally, for our test method, we'll choose Estimate the proportions separately. Then click OK, and click OK again. And here are our results. We get the sample proportion, or p hat, for the two different groups. We get a 95% confidence interval for the difference. And we get the p-value for the two-proportion z-test. That's 0.025. So at the 5% significance level, there is enough evidence to say that there's a difference in the proportions of all younger people versus all older people who complete the vaccine. You might notice this other p-value down at the bottom. That's a p-value for an alternative method for testing hypotheses for proportions, called Fisher's exact test. This method tends to be better when your sample sizes are small, meaning that n times p times 1 minus p is less than or equal to 10. So in this case, that would give us a p-value of 0.049, still giving us the same conclusion, but with slightly less confidence because the p-value is slightly closer to 0.05.